Okay, so electric energy and electric potential energy and electric potential is the next title. So first, I'm going to define the gravitational potential energy. We know in the chapter 3, I think you studied about the potential energy or work, chapter 4, pardon. If an object or mass falls a distance of h, this object loses its gravitational potential energy. So its gravitational potential energy decreases when it falls from this point to that point by an amount of m times g times h. So when it goes up, it gains gravitational potential energy, falls down, it loses gravitational potential energy by an amount of mgh. So then, if I say that when object falls down in the direction of the gravitational field is downward, so its gravitational potential energy decreases, so it changes by negative mgh. This negative sign indicates that gravitational potential energy decreases. So we can make an analogy from gravitational field to electric field. So in electric field, when you release a charge QO in the electric field, you know, test charges are generally assumed to be positive. They are assumed to be positive. So this test charge moves in the direction of the electric field because there will be an electric force acting on the charge, which is equal to Q times E. Remember the previous section. So here on the mass, mg is acting. Here on charge, Q times E is acting. So these two forces causes, one of them causes m to displace, another one causes charge to displace. Now, gravitational force does work on the mass. Here, electric force does work on the charge. So the uniform electric field does work on the positive charge by moving the charge in the direction of the electric field. So causes a decrease in the electric potential energy. Now this force, gravitational force, causes a decrease in gravitational potential energy. Electric force causes a decrease in electric potential energy. In fact, equations are very similar. So change in gravitational potential energy is negative mgh. Change in electric potential energy of the system is again negative. Instead of m, we are going to put Q. Instead of G, we are going to write E. Instead of H, we are going to write D, distance traveled by the object. So change in electric potential energy of the system is equal to negative QO, which is the charge moving the electric field, times electric field multiplied by distance traveled by the charge. So these two equations are very similar to each other. Now let's solve a practice problem. It says as a particle moves 10 meters along an electric field of strength 75 Newton per coulomb, its electric potential energy decreases. When it says you are going to write the number of the electric energy as negative. 4.8 times 10 to the power negative 16 joule. What is the particle's charge? So distance traveled by the object is equal to 10 meters. So you can write it QED or you can write QER. In your book, it's written, I think it is D, so not R. So let's change it to D. Distance traveled by the charge is 10 meters. So in electric field of 75 Newton per coulomb, its electric potential energy decreases. For that, as I put the negative sign here, negative 4.8 times 10 to the power of negative 16 joule. So calculate the charge. The equation for the change in electric potential energy is what? Delta E potential energy is equal to negative QO ED. So we will find what is QO. So then you have to divide both sides by E times T and simplify E and D. QO becomes in this case negative of delta PE potential energy, change in potential energy, divided by E times D. So change in electric potential energy is given at negative 4.8 times 10 to the power negative 16. E is given as 75 Newton per coulomb. Distance traveled by the charge is given as 10. So when you do this calculation, you will get the charge as positive 6.4 times 10 to the power of negative 90, because negative times negative becomes positive. So it's a positive charge. because we know that if a positive charge is released inside an electric field, its potential electric system's electric potential energy decreases. So this is a general case when you release a positive charge inside an electric field. Electric potential energy of the system decreases. Charge move in a way that electric potential energy of the system will decrease. So now, after defining the electric potential energy, we are going to define electric potential difference. But now here, I said that if you release a positive charge inside an electric field, it moves in the direction of electric field and its electric potential energy decreases. Now, assume that you are going to put charge between to point K and it will move in the direction of the electric field because it's a positive test charge, so it moves in the direction of the electric field from K to M. And the change in electric potential energy will be QO, which is QO times E times R or D, whatever. So distance D or R, we can say that. But if you put a charge to QO, if you double the charge, in this case, decrease in electric potential energy also doubles. So 2QO ER. If you put a charge right here at point K, 3Q, change in electric potential energy also becomes triples 3 times QO ER. So, however, when you divide this change in electric potential energy by the charge, you get the same number. So, let's divide it. 3QO ER divided by 3QO. So, they simplify. So, you got ER. So right here 2QO ER divided by charge 2QO. So they simplify, you got ER. So right here QO ER divided by QO, they simplify, you got ER. So this ER is something which is independent of the charge. It only depends on the electric field. That the quantity is known as the potential difference between K and M. So, potential difference between K and M can be calculated by dividing the change in electric potential energy by the charge which is moving between these 2 points. Now, I'm going to define it again. So, potential difference is a measure of difference in electric potential energies between 2 positions in space divided by the charge. So we are going to divide change electric potential energy by the charge moving between these 2 points. We will find the potential energy potential difference between these 2 points. So as the charge moves from K to M, its potential energy changes by delta EPE or delta PEE. So the potential difference between these 2 points will be equal to delta EPE divided by charge QO, which is moving between these 2 points. So potential difference and potential change in potential energy is related to each other, as you see. So can we get the unit of electric potential difference? Yes, we can. Potential difference is known as the unit of potential difference volt. 1 volt is equal to, what is unit of electric potential energy? Joule. What is unit of charge? Coulomb. 1 volt is equal to 1 joule per coulomb. So this is important also for 12th grade. So now we'll turn back to the question again. So question 2 is related to question 1. What is the potential difference between the initial and final locations of the particle in problem 1? It says. So we know electric potential energy decreases. It's given in the question as 4.8 times 10 to the power negative 16. So it decreases for negative 4.8 times, it changes negative 4.8 times 10 to the power negative 16 joule. At the charge we calculated, which is equal to 6.4 times 10 to the power negative 19 coulomb. Now calculate the potential difference between these 2 points, K and M. We will find what is the potential difference between K and M. So the potential difference between these 2 points is equal to change in electric potential energy of the system while QO moves from K to M, which is equal to that number, divided by charge itself, QO, it is this number. So negative 4.8 times 10 to the power negative 16 divided by 6.4 times 10 to the power negative 19, answer becomes negative 750. So this negative sign indicates something. Why? What does it indicate? The change is negative, which means the potential difference is decreasing while you move from K to M. Yani point K has a greater electric potential than point M. So point M is at the electric potential which is 750 volt less than point K, or point K is at an electric potential which is 750 volt greater than point M. So then we can understand if it is negative, the particle is moving from a point at high electric potential to a point of low electric potential. So the same thing can be defined for batteries too, because batteries also have one negative, one positive terminal. In a battery, positive terminal is at a great electric potential, negative terminal is at a low electric potential. So between the terminals of the battery, there will be a potential difference, and this potential difference will be written on the battery as, for example, 1.5 volt. So this 1.5 volt indicates that this type of water means a potential difference across its terminals such that the positive terminal has an electric potential that is 1.5 volt higher than the electric potential of the negative. So this terminal has a electric potential which is 1.5 volt greater than that one, negative side. Assume that if you take the negative as 0, so positive end becomes 1.5. So if the negative terminal of the battery is at 0 potential, the positive terminal will have a potential of 1.5 volt, because it is greater from the negative side by an amount of 1.5 volt. Next question. An electron moves 4.5 meter in the direction of the electric field. Normally, this is not tendency of electron. When you release an electron inside an electric field, electron's tendency is to move in the opposite direction of electric field. So then if it is moving in the direction of electric field, you force the electron to move in the direction of electric field. So then distance traveled by the electron is 4.5 meters. Electric field strength is given as 325 Newton per coulomb. So because it's an electron has a negative charge, negative 1.6 times 10 to the power negative 19 coulomb. What is the change in electric potential energy? Delta EPE is the question. So change in electric potential energy is equal to, remember the equation, negative QOED. So because you force the electron to move in the direction of electric field, you should use this equation. So negative times negative becomes positive. So negative, what is charge of an electron? 1.6 times 10 to the power negative 19. What is the electric field? 325. What is the distance traveled electron? 4.5 meter. Multiply them all, then you got the answer as positive 2.34 times 10 to the negative 16 joule. So this is an increase in electric potential energy. As you see, it's positive. So and then if you say that if you force a negative charge to move in the direction of electric field, system's electric potential energy increases. How? You are doing work on the electron by forcing it to move in the direction of electric field. Okay, so when we define electric potential energy, we assume that electric field is uniform, right here as you see here. But electric field is not uniform everywhere. For example, it's a positive charge. Around a positive charge, electric field is greatest at the closer point, but smaller in the farther point. As you see, it's not uniform. So, however, electric field is around the positive charge is not uniform. So to set up a uniform electric field, you use generally two parallel conducting plates, as you see here. One plate, another plate. And between these two plates, now you can form a uniform electric field. What does uniform electric field mean? It is the electric field, the same everywhere in magnitude. How can you form this electric field? You are going to connect each plate to one terminal of a battery. This is a battery, and this battery has a potential difference. So if you connect one plate, positive terminal of the battery to one plate, this plate becomes positively charged. If you connect negative terminal of the battery to another plate, this plate becomes negatively charged. Then electric field will be formed from positive to negative, and this electric field is uniform, and we can calculate the equation for this electric field because this is different than the electric field of a point charge, because electric field of a point charge around the space is K times Q over R or D, what use, I don't know, distance, R squared or D squared. As you see, as the distance changes, electric field changes for point charges, but for parallel plates, no. Right here in the interior region, electric field is uniform, yani constant everywhere. Now let's get this equation for this electric field. We know that if a test charge moves from this point to that point, its electric potential energy changes. The change in electric potential, if divided by the charge itself, yani change electric potential divided by charge, we can calculate the potential difference between these two plates. We know that if a charge moves in a uniform electric field, in the beginning, its electric potential energy changes by negative QOED. If we divide this negative QOED by QO, so these two QOs simplify, and you get the equation for electric field. So get the other side as division. Electric field becomes delta V over delta T, which means electric field, uniform electric field between two parallel plates can be calculated by the equation, which is delta V over D. What is delta V? The battery connected across the terminal of the parallel plate. What is the separation between the plate? What does it mean? If you make plates closer, which means D decreases, electric field becomes greater in magnitude. If you increase the potential difference, electric field between the plate increases. So this equation is important. So it's the equation for calculating electric field, which is uniform between two parallel plates. Another thing you are going to meet in the 12th grade, this definition. So electric field has two units. One of them is coming from this. Electric field is equal to force divided by charge, which is Newton per Coulomb in the chapter section 2 you studied. Another one is coming from here. What is potential difference? Volt. What is distance unit? Meter. Volt per meter. Then we can say that 1 Newton per Coulomb is the unit of electric field from chapter section 2 is equal to 1 volt per meter. So these two units are equal. Don't forget this because you are going to meet this in the 12th grade. So now let's solve a problem. A proton is released from rest in a uniform electric field. Uniform, yani parallel plate, with a magnitude of 4 times 10 to the power 4 volt per meter. As you see, unit of electric field is given volt per meter for parallel plate. The proton is displaced. First, let's record the electric field is 8 times 10 to the power 40 volt per meter. If the proton is displaced by 0.5 meter as a result, so find the potential difference between the proton's initial and final position. So distance is given, we will find delta V. It's easy because electric field is equal to negative delta V divided by E. So delta V becomes negative E times D. So now let's write it now. Negative E. What is E? Electric field is given 8 times 10 to the power 4. What is distance traveled by the proton? 0.5. Multiply them, you will get the electric potential difference between the plates or initial and final positions. Now, second part B. Find the change in electric potential energy of the proton as a result of this displacement. It is also easy because we know that potential difference is equal to change in potential energy divided by charge moving between these 2 points. Cross multiply them, change in potential energy becomes Q times change in electric potential difference. So Q is its proton positive 1.6 times 10 to the power negative 19. So delta V is negative, then multiply them, you will get the change in electric potential energy as negative, which means electric potential of the system decreases as proton moving between these 2 points. So one more thing we are going to study. Now, right here electric field is constant, so constant everywhere. Another one is this one. So electric field is not constant around here, as you see. Electric around the positive charge, any charge, it can be negative 2. And this charge also produces a potential, electric potential at any distance from the charge itself. A point charge Q created electric potential at a distance r. This electric potential is given by the equation V is equal to kq over r. Now it is very similar to electric field equation. Electric field's equation is, remember, this charge produces an electric field at a distance r by kq over r squared. So electric field at this point is kq over r squared, but electric potential at that point is kq over r. So this charge produces an electric field, electric potential at any point distance r, which is equal to kq over r. So is it useful for the 10th class, 11th, 12th grade? No, we are not going to use this in 12th grade, but you should know every charge produces or creates an electric potential in the space, and this electric potential is changing or decreasing as the distance from the charge increases. All right, now we go on another title, which is capacitance and capacitors, because capacitors are mostly studied by parallel plate. Now we are going to use the parallel plate information. But before starting that, we define what capacitance is. Now there are two parallel plates, as you see here. As the amount of electric charge on the parallel two plate increases, the electric field intensity between the plate also increases. Why? Because when I put a positive here and negative here, an electric field formed. So from every positive to negative, there is an electric field formed. When you increase the number of charge on the plate, of course, you should expect that electric field increases. So when you put more charges, so you are going to form more electric field. So then you can say that electric field is proportional to charge of the parallel plate or charge of a conductor. If you increase the charge of the conductor, electric field spreading out from this conductor will increase. Another equation is this. We just studied about parallel plate. E is equal to negative delta V over D. So if you cross multiply them, you can get delta V is equal to negative E times T. What does it mean? Yes, if you increase the charge, electric field increases. So increasing electric field results in an increase in electric potential difference or electric potential. So when you increase the charge or parallel plate or any conductor, electric field of this split out from this conductor increases. Also electric potential of this conductor increases. Now, directly proportional, in fact. If this doubles, then this doubles, that doubles. So say that initially charge is Q, electric field is E, potential difference of the conductor is V. So then ratio Q over V. But if you double the charge, electric field doubles, potential of the sphere conductor also doubles. But ratio doesn't change. 2Q over 2V, 2Q over 2, again Q over V. If you triple the charge, electric field triples, electric potential also triples. But ratio also constant, 3Q over 3V, Q over V. This Q over V gives a property of this conductor. That property is known as capacitance. Capacitance of this conductor. What does capacitance means? How big charge can be stored in a conductor. How great amount of charge can be stored in a conductor. Capacitance is defined as the ratio of the net charge on a conductor to the electric potential difference of that conductor. So we are going to divide total charge on this conductor by the electric potential of this conductor, and we will find capacitance of this conductor. So then capacitance, again, let's define ability of a conductor to store electric charge. If it stores a greater amount of electric charge, we can say that its capacitance is high. If it stores smaller amount of electric charge, we can say that its capacitance is low. So what is unit of capacitance? Farad. Equal to what? Coulomb per volt. 1 farad is equal to 1 coulomb per volt, coming from this equation. But farad is a very big quantity. For that, as in generally microfarad or picofarad is used, but microfarad is more frequently used. In the 12th grade, also you are going to meet this. 1 microfarad is equal to 10 to the power negative 6 farad. Don't forget this. Capacitance of a conductor depends on its shape and some other certain properties of the conductor. So what does it mean? If the conductor is a sphere, if it is a cylinder, if it is a parallel plate capacitor, in this case, capacitance will be different. So suppose
An isolated conductance sphere, now assume that there is a conductor sphere, of radius r and charge on this sphere is q. The electric potential in this case becomes, remember, electric potential of a charge q is previous equation q k over r. So on the surface of the sphere. What about the capacitance? C is equal to q divided by delta v. If you substitute this delta v here, you get the capacitance of a sphere, which is equal to q divided by k q over r. So this q simplify, you get equation r over kc. What does it mean? If you make the sphere radius greater, capacitance increases, which means if you make or use a sphere which is larger in size, its capacitance is great. This equation indicates that the capacitance of a sphere increases as the size of the sphere increases. Greater sphere, stores greater electric charge. Smaller sphere stores smaller electric charge. Because Earth is so large, it has an extremely large capacitance. Thus, Earth can provide or accept a large amount of charge without its electric potential changing too much. So, question. A 4 microfarad capacitor is connected to 12-volt battery. So, C is equal to 4 microfarad. So, what is the potential difference? Delta V, 12-volt battery. What is the charge on each plate of the capacitor? So, calculate Q. Very easy. C is equal to Q divided by delta V. But the question is calculate Q. Q becomes C times delta V. C is given as 4 microfarad, but convert it to farad by multiplying 10 to the power of negative 6 multiplied by delta V, 12. When you multiply them, you will get the answer as Coulomb. So, capacitance is ability of a conductor to store electric charge. But there are some special instruments manufactured in the technology known as capacitors. Capacitors are the devices. Don't confuse. Capacitance is ability of a conductor to store. It's a phenomenon. Capacitance is a phenomenon, but capacitor is a device, such a device. So, capacitor is a device that is used to store electric potential energy, electric energy. So, a typical capacitor consists of two parallel plates here. That's why we started parallel plates here. So, two parallel plates separated by small distance. This type of capacitor is called parallel plate capacitor. So, when you connect them, one plate of this capacitor to one terminal of the battery, other plate to other terminal, this capacitor is charged. So, the plate connected to positive becomes positively charged. The plate connected to negative terminal becomes negatively charged. And there will be a potential difference, which is exactly the same as the battery. If the battery is 1.5 volt, potential difference across the capacitors also becomes 1.5 volt. And we say that this capacitor is charged by Q, whose capacitance is Q, potential difference is delta V. Then we can use this energy for other purposes. So this capacitor gets the energy, then gives back when you need it. Okay, so as I said, the basic and most simple capacitor is parallel plate capacitor. So capacitance of a parallel capacitor is depends on two things. One of them is the area. So if the area is large, so then space for the charge will be great. So then capacitance will increase. The area of the capacitor increases, the amount of charge Q on the surface of the capacitor increases, so capacitance also increases. But if you make the closer the plates, as the plates get closer and it decreases, electric field increases and capacitance also increases. So when you make the plate closer, its capacitance also increases. So then we can say that capacitance of a capacitor is directly proportional to area of the plate, but inversely proportional to separation between the plate. So C is proportional to what? A over D. Directly proportional to area, inversely proportional to separation between the plates. When you put a constant here, make this proportionality as an equality, C is equal to E O epsilon, A over D. This Greek letter epsilon represents a constant, which is called permittivity of the medium, that medium. So permittivity. It has a magnitude of 8.85 times 10 to the power negative 12. Negative 12 Coulomb square times Newton times meter square for vacuum or air. But for different materials, this permittivity is different. In many parallel plate capacitors, the spaces between the plates is filled with cut material which is called dielectric. This is also known as dielectric constant. If a dielectric is inserted between the parallel plates, you can increase the capacitance of a capacitor. How? When a dielectric is inserted inside between the plates, so this dielectric can be rubber, glass, or waxed paper, capacitance increases. How? Because this capacitor, this inserted dielectric material decreases the electric field between the plates. If electric field decreases, potential difference between the plates decreases. If potential difference decreases because you keep the total charge constant, capacitance of the capacitor also increases. Okay, so now a parallel plate capacitor has a charge of 6 microcoulomb. So Q is equal to 6 microcoulomb. Of course, you should change to the coulomb again, 6 times 10 to the power of negative 6 coulomb. When charged by a potential difference delta V, which is equal to 1.25 volt. Find the capacitance C. We know that C is equal to Q divided by delta V. So Q is 6 times 10 to the power of negative 6 divided by delta V 1.25. When you divide these two numbers, you will get the capacitance as farad. Another thing is capacitors are used for storing electric energy. Don't forget this. Capacitors are used to store electric energy. It gets energy from the battery, then when needed, it gives it back again. So we can now write the equation for stored in a capacitor. A charged capacitor stores electrical potential energy because it requires work to work the charges through a circuit to opposite plates of capacitor. The work done on the charge is measure of the transferred energy. So now remember, when the potential difference on the capacitor increases, charge on the capacitor also increases. If potential difference is V, charge is Q, say that. If potential difference becomes 2V, it's 2Q. 3V, 3Q. So you get a direct relation between the potential of the conductor and charge. So this area right under the graph will give us the energy stored in the capacitor. How can you find this area? This area is a triangle. Triangle area is one side multiplied by other perpendicular side divided by 2. One side is Q, other side is V. Q divided by delta V divided by 2 is the energy stored in a capacitor. But you can write this equation in two different forms. We know delta V is equal to Q divided by C. Instead of delta V, you can write here Q divided by C. You get this equation. So potential energy stored in a capacitor is Q squared divided by 2C. Or instead of Q, you can write Q C times delta V by cross multiplying this. C times delta V is the Q multiplied by delta V divided by 2. So it becomes C delta V squared over 2. So these two equations are identical, but according to the given of the problem, you can use one of the equations you choose.